March 1910, Southern Railway Yards, Washington, D.C. A fireman named Thomas Breslin climbs onto locomotive number 1102 for a routine morning inspection. The boiler has been warming for 2 hours, pressure building steadily toward operating range. He never sees the cracks spreading through the crown sheet. He never hears the warning hiss of escaping steam. One moment he's checking the water glass, the next the boiler detonates with the force of 20 tons of dynamite. The blast is heard 12 miles away. Pieces of the locomotive are found 3 blocks from the yard. Breslin's body is recovered in sections over the following week. The locomotive that killed him was a simple design, no compound expansion, no complex valve mechanisms, no intricate moving parts. It was supposed to be safer. By any conventional engineering standard, Locomotive 1102 was unremarkable. It had 2 cylinders, basic Stephenson valve gear, a standard firebox. The boiler looked like every other boiler rolling out of American factories in that era, a long, cylindrical pressure vessel wrapped in steel plate and studded with rivets. There was nothing about its external appearance that suggested danger. No warning placards, no special handling procedures, no visible indication that climbing aboard meant accepting a particular kind of risk. It was, the manufacturers insisted, elegantly simple. It was also a bomb. The simplicity was the problem. What Locomotive 1102 represented was a fundamental miscalculation in American railroad engineering, a decision made in boardrooms and drawing offices that would be paid for in blood and shattered metal across 3 decades. These simple expansion locomotives, built by the thousands between 1890 and 1920, achieved something remarkable. They delivered the power of expensive compound engines at a fraction of the cost. They required less maintenance, less skilled labor, less time in the shops. They made railroad companies extraordinarily profitable. They also killed more workers than any other locomotive design in American history. By 1915, the pattern was undeniable. Boiler explosions involving high-pressure simple locomotives occurred at rates that dwarfed their compound counterparts. Firemen and engineers died in rail yards, on main lines, in switching operations, often without warning, frequently without survivors to explain what went wrong. The explosions were catastrophic. A typical compound locomotive failure might blow a safety valve or crack a steam line. When a high-pressure simple failed, it vaporized. The energy release was comparable to naval artillery. What made a simpler machine so much more dangerous? The answer lay not in what these locomotives had, but in what they lacked. Every component removed in the name of simplicity, every safety margin eliminated for efficiency, every automatic control replaced with manual operation created a potential failure point. The simple locomotive was cheaper to build because it transferred risk from the machine to the men who operated it. It asked human beings to manage forces that required split-second precision and perfect judgment under conditions of heat, noise, vibration, and fatigue. And when human beings failed, as human beings inevitably do, the machine did not merely break down, it exploded. The problem facing American railroad companies in the late 1880s was simple to state and nearly impossible to solve. The nation's rail network was expanding at an unprecedented rate. Freight tonnage was doubling every decade. Passenger traffic demanded higher speeds over longer distances. The locomotives pulling these loads needed to be more powerful, but the existing technology was reaching its limits. Compound expansion engines, the most advanced design of the era, could deliver the required power. They were also expensive to build, complex to maintain, and required skilled mechanics who commanded premium wages. Railroad executives wanted the performance of compound engines without the costs. They wanted power without complexity. They wanted, in essence, the impossible. Compound locomotives achieved their efficiency through an elegant thermodynamic principle. Steam expanded first through a high-pressure cylinder, then passed into a larger low-pressure cylinder for a second expansion. This 2-stage process extracted more work from each pound of steam, which meant less coal burn per mile traveled and lower operating pressures in the boiler itself. A typical compound operated at around 160 pounds per square inch. The design was sophisticated, almost baroque, in its mechanical intricacy. It worked beautifully. It also cost nearly 30% more than a simple expansion engine and required maintenance schedules that kept locomotives out of revenue service for extended periods. The simple expansion engine used a different approach. Steam entered the cylinders directly from the boiler at full pressure, expanded once, and exhausted to atmosphere. Fewer components, fewer failure points, lower manufacturing costs, reduced maintenance requirements. The problem was power. A simple engine operating at 160 psi could not match the work output of a compound. The cylinders would need to be impossibly large, or the locomotive would simply be inadequate for mainline service. The solution seems straightforward. If the simple engine needed more power, increase the pressure. Run the boiler at 200 psi instead of 160. Run it at 220. Push the steam pressure high enough, and a simple two-cylinder engine could match or exceed compound performance at a fraction of the cost. On paper, the mathematics worked perfectly. In practice, the mathematics ignored reality. Boiler technology in the 1890s was based on riveted steel plate construction. The techniques had been refined over decades, but they were fundamentally the same methods used to build the first locomotives in the 1830s. Plates were formed, overlapped, and joined with thousands of rivets. Driven by hand, the resulting pressure vessel was strong, but it was not uniformly strong. Stress concentrated at rivet holes. Seams were potential weak points. Thermal expansion and contraction caused gradual metal fatigue. A boiler operating at 160 psi had safety margins built into every dimension. A boiler operating at 220 psi operated at the edge of material failure, and the edge was not a fixed line, but a moving target that shifted with temperature, load, metal quality, and time in service. Railroad companies understood the risks, but the economic pressure was overwhelming. A compound locomotive cost $18,000. A high-pressure simple cost $12,000. Over a fleet of hundreds of locomotives, the savings were measured in millions. Maintenance costs told a similar story. Compound valve gear required constant adjustment by skilled mechanics. Simple valve gear could be serviced by less experienced workers at lower wages. The compound engine was an engineering masterpiece. The simple engine was a business decision. The assumption, rarely stated but always present, was that crews could manage the higher pressures. Firemen would monitor water levels more carefully. Engineers would watch the pressure gauge more closely. Human attention would substitute for mechanical safeguards. This assumption ignored what actually happened in a locomotive cab during operation. The environment was hostile to precision. Temperatures regularly exceeded 120 degrees Fahrenheit. Noise from the exhaust made communication nearly impossible. Vibration shook every surface. Smoke and steam obscured visibility. The firemen worked in constant motion, shoveling coal into the firebox, adjusting dampers, monitoring multiple gauges, adding water to the boiler. The engineer managed throttle, brake, reverser, and watched the track ahead while maintaining schedule. Both men were making continuous decisions under physical stress and cognitive load. Asking them to manage steam, pressures that allowed no margin for error, was asking them to be superhuman. The specification seemed achievable. Build a simple locomotive with a high-pressure boiler, larger cylinders, and straightforward valve gear. The result would be powerful, economical, and reliable. The cost would be paid in blood, though the accountants calculating construction budgets never entered that figure on their ledgers. The task fell to locomotive builders across America and Britain, manufacturers who understood the engineering compromises they were making, but built what the market demanded. They were not building transportation. They were building pressure vessels that operated at the threshold of catastrophic failure, and they were putting men inside them. The engineers who designed high-pressure simple locomotives made 3 decisions that determined everything that followed. Each decision seemed reasonable in isolation. Together they created a machine that killed with mechanical precision. The first problem was boiler pressure. A simple expansion engine needed higher steam pressure to match the power of a compound. The physics were straightforward. Pressure equals force, force equals work. Work equals the ability to pull heavy trains up steep grades at acceptable speeds. Standard compound locomotives operated at 160 pounds per square inch. The new simple designs pushed that number to 200, sometimes 220, occasionally higher. The engineers knew what they were doing. Pressure does not increase in a straight line. When you double the pressure inside a boiler, you quadruple the stress on the metal containing it. A boiler rated for 160 psi operates with substantial safety margin. A boiler running at 220 psi operates near the absolute limit of what riveted steel plate can withstand. The metallurgy of the era could not reliably handle these sustained pressures. Boilerplate was manufactured to varying standards. Quality control was inconsistent. A plate that tested perfectly in the factory might contain microscopic flaws that propagated under thermal stress. The rivets holding the plates together were driven by workers whose skill varied from master craftsman to barely trained apprentice. Every rivet hole was a stress concentration point. Every seam was a potential crack initiation site. The safety margins that had protected crews for decades were eliminated in the pursuit of performance. The solution was simple: use higher pressure. The problem was equally simple. The boilers were not built for it. The second problem was valve timing. Compound engines had a built-in elegance. Steam flow between the high-pressure and low-pressure cylinders was partly self-regulating. The system had inherent stability. Simple engines had no such luxury. The Stephenson valve gear that controlled steam admission was mechanically straightforward, just eccentrics and rods and links that opened and closed valves in precise timing with piston movement. It was also completely unforgiving. If the valve timing was off by even a few degrees, the consequences cascaded through the entire system. Steam entered the cylinder at the wrong moment. Expansion was uneven. Metal components experienced thermal shock, heating and cooling in rapid cycles that caused fatigue and failure. The valve gear had to be adjusted perfectly and maintained perfectly, but maintenance schedules were determined by accountants, not engineers, and perfect adjustment required time that cost money. They approached the problem not as safety engineers, but as efficiency engineers. The question was never whether the design was safe. The question was whether it was profitable. Manual control replaced automatic regulation because automatic systems added cost and complexity. The engineer and fireman would manage steam flow, valve timing, and pressure regulation through constant attention and perfect judgment. There was no room for error, no forgiveness for a moment of distraction, no backup system. When human beings made human mistakes. The third problem was water level control. Every steam locomotive boiler depended on maintaining water above the crown sheet, the metal plate forming the top of the firebox. If water level dropped and the crown sheet was exposed to direct flame, the metal overheated in seconds. At lower pressures, this caused damage and required repair. At high pressures, it caused something different. The overheated metal weakened just as the steam pressure pushing against it was at maximum. When the crown sheet failed, thousands of gallons of water at 400 degrees Fahrenheit instantly flashed to steam. The expansion ratio was 1,600 to 1. The boiler did not leak or crack, it detonated. Compound locomotives used automatic water level controls and redundant monitoring systems. These added weight and cost. High pressure? Simples relied on the fireman watching a glass tube that showed water level inside the boiler. The fireman was also shoveling coal, monitoring steam pressure, adjusting dampers, and working in an environment of extreme heat and constant vibration. He was expected to glance at the water glass every few minutes while performing heavy physical labor. If he missed a low water condition for 60 seconds, everyone aboard could die. When a high-pressure simple boiler failed, it did not just break, it detonated. The energy release was comparable to a large artillery shell. The boiler itself became shrapnel, pieces of steel plate traveling at ballistic velocities. The steam cloud that erupted was superheated and under pressure, capable of scalding flesh from bone at 50 yards. Men did not die from these explosions. They were erased. The locomotives looked safe from the outside. They had the familiar shape, the expected components, the reassuring solidity of thousands of tons of steel and iron. Nothing in their appearance suggested danger. But appearance meant nothing. What mattered was the pressure vessel operating at its absolute limits, controlled by men who could not afford a single mistake, ever. Production of high-pressure simple locomotives began in earnest in the early 1890s. Baldwin Locomotive Works in Philadelphia built thousands. The American Locomotive Company produced them by the hundreds at factories across the Northeast. British manufacturers, including the North British Locomotive Company, exported them worldwide. The exact numbers remain difficult to establish because many smaller builders kept incomplete records and some documentation was destroyed in later decades. But conservative estimates suggest at least 15,000 high-pressure, simple locomotives entered service between 1890 and 1925. They were economic successes. Railroads saved millions in construction and maintenance costs. Shareholders received healthy dividends. The locomotives proved they could haul the loads and maintain the schedules that railroad companies demanded. For the first few years, nothing seemed wrong. The first operational deaths came quietly, attributed to operator error or mechanical failure or simple misfortune. A boiler explosion was not unusual in railroad operations. Locomotives were dangerous machines, men died. The industry accepted this as the cost of progress. But by the early 1900s, a pattern emerged for anyone willing to see it. High-pressure, simple locomotives were failing at rates that exceeded all previous experience. August 1905, Pennsylvania Railroad yards outside Pittsburgh. Locomotive 3847 was preparing for an evening freight run. The crew was experienced, the engine recently serviced. As the locomotive began moving, the fireman noticed water level dropping in the glass. He opened the injector to add water to the boiler, standard procedure, nothing unusual. What he could not see was that the injector valve had partially failed and water was entering the boiler slower than steam was being consumed. The crown sheet began to overheat. 60 seconds later, the boiler exploded. The blast killed 6 men outright and injured 14 others. The fireman was thrown 200 feet and died before reaching the hospital. The engineer survived, but lost both legs. The locomotive's boiler was found in 3 pieces scattered across the yard. Witnesses described the sound as like artillery fire, a crack so loud it shattered windows a quarter mile away. February 1911, Great Northern Railway in Montana. A heavy freight was climbing a steep grade through mountain terrain. The engineer was managing throttle carefully, trying to maintain momentum without overworking the locomotive. The fireman was shoveling coal as fast as he could, feeding the intense demand for steam. Neither man realized the boiler was experiencing thermal runaway, a condition where steam demand exceeded the boiler's ability to maintain stable pressure and temperature. The metal was cycling through extreme thermal stress with every shovel of coal, a crack that had been slowly propagating through the crown sheet for weeks suddenly failed. The boiler exploded with enough force to throw the entire locomotive off the rails. The engineer, positioned further forward in the cab, survived with severe burns. The fireman, standing directly over the firebox, was killed instantly. Investigators found the boiler 200 yards from the track, embedded in the hillside. December 1913, London and Northwestern Railway. The locomotive was operating normally by all observable measures. Pressure was steady, water level was correct, the crew was following standard procedures. There had been no indication of any problem. The boiler had passed inspection 3 weeks earlier. At 2:47 in the afternoon, during routine switching operations in the yard, the boiler exploded. The inquest determined death by misadventure, the standard verdict when no specific cause could be identified. What the investigation missed was that the boiler had been in service for 11 years. The metal had been heated and cooled, stressed and released, cycled through temperature extremes tens of thousands of times. Microscopic cracks had formed at rivet holes and propagated slowly through the plate. The boiler had not failed because anyone did anything wrong. It failed because the metal was tired. The pattern repeated across North America and Britain. Experienced crews following proper procedures died in explosions that gave no warning. The failures were not concentrated in any particular railroad or region. They occurred in switching yards and on main lines during routine operations and emergency situations, with new locomotives and old ones. What unified them was the design. High-pressure, simple locomotives were exploding at approximately 3 times the rate of compound locomotives. The energy released in these explosions was consistently higher, the damage more catastrophic, the survival rate lower. Railroad workers began to understand what the companies refused to acknowledge. Certain locomotives were death traps. A whisper network developed among firemen and engineers. Men traded information about which engine numbers to avoid, which designs had the worst reputation, which railroads were most cavalier about safety. Some workers refused assignments on high-pressure simples, accepting discipline or termination rather than climbing aboard. Insurance companies noticed the pattern before railroad management did. Premiums for coverage on high-pressure simple operations began rising. The actuarial tables told a story that words could not. These machines were killing people at rates that exceeded normal industrial hazards. If you are finding this interesting, a quick subscribe helps more than you know. The bodies continued accumulating, but the locomotives continued operating, because stopping them would mean admitting that the pursuit of efficiency had been purchased with human lives. The beginning of the end came not from engineering insight, but from political pressure that could no longer be ignored. March 1911, San Antonio, Texas. A Southern Pacific locomotive exploded in the downtown rail yard during morning rush hour. The blast killed 11 people, including 3 bystanders who had been walking past the yard fence. One victim was a child on her way to school. The explosion made front-page news across the nation. Photographs of the devastated rail yard appeared in newspapers from New York to San Francisco. The public outrage was immediate and sustained. Railroad companies could dismiss worker deaths as occupational hazards, but they could not dismiss dead civilians. Congress demanded answers. The Interstate Commerce Commission, which had largely ignored locomotive safety, suddenly found itself under intense scrutiny. The ICC investigations that followed were meticulous and damning. Engineers testified about pressure limits being exceeded routinely. Workers described maintenance schedules driven by cost rather than safety. Metallurgists explained how boilerplate failed under sustained high-pressure operation. The statistical evidence was overwhelming. High-pressure, simple locomotives were failing at rates 3 to 4 times higher than compound designs. The investigations produced hundreds of pages of testimony and technical analysis. The conclusions were unambiguous. The pursuit of economy had created machines that killed the men who operated them and occasionally killed innocent bystanders as well. Labor unions, which had been fighting for locomotive safety standards for decades, finally had political leverage. The Brotherhood of Locomotive Engineers and the Brotherhood of Locomotive Firemen and Enginemen demanded mandatory pressure limits, required safety equipment, and enforceable inspection standards. Strikes were threatened. Some were carried out. Railroad companies, facing both regulatory pressure and labor action, began changing their practices not from sudden concern for safety, but from cold calculation. That the costs of resistance had finally exceeded the costs of compliance. The technical evolution that followed revealed the fundamental dishonesty of the original simple locomotive premise. Engineers developed automatic water level controls that shut down the locomotive if water dropped below safe levels. These systems added weight and complexity. Improved safety valves with redundant backup systems became mandatory. More complexity. Better metallurgy allowed boilerplate to handle high pressures more reliably, but the improved steel cost more and required more sophisticated manufacturing. Mandatory pressure limits were enforced through regular testing and inspection. Firemen required certification and training that took weeks instead of days. By the mid-1920s, a properly equipped high-pressure simple locomotive incorporated nearly as many safety systems as a compound engine. The original promise, power through simplicity at reduced cost, had been a lie. You could have power, and you could have safety, but you could not have both cheaply. The final accounting of deaths is incomplete because many railroads destroyed or concealed records that documented the true cost of their economic decisions. Conservative estimates based on ICC reports, newspaper accounts, and union records suggest between 800 and 1,200 workers died in boiler explosions directly attributable to high-pressure simple locomotive design flaws between 1890 and 1925. Thousands more were injured, many permanently disabled. Burns, lost limbs, blindness, psychological trauma that we now recognize as post-traumatic stress, but that era dismissed as weakness. The human cost extended beyond the immediate victims. Families lost breadwinners, communities lost skilled workers. Children grew up without fathers. The economic damage to individual lives was never calculated in the railroad company ledgers that showed such healthy profits. Some of the dangerous locomotives remained in service into the 1940s, operating on branch lines and secondary routes where regulatory oversight was minimal and worker protections were weakest. The machines that should have been scrapped in 1915 were still killing people in 1943, though by then the deaths were rare enough and remote enough that they attracted little attention. The industry had moved on to diesel-electric locomotives that eliminated steam boilers entirely. The era of steam was ending, and with it, the immediate danger, but the lessons should have echoed forward. What the high-pressure simple locomotive revealed about industrial progress was this: efficiency and safety are not naturally aligned. The market does not automatically optimize for human welfare. The simplest solution is often simple only because it transfers complexity and risk from the machine to the operator, from the owner to the worker, from capital to labor. The pattern has repeated across every subsequent industrial revolution. Early automobiles with minimal safety features, aircraft designed for performance with inadequate structural margins, industrial machinery that maximized output while minimizing safeguards. In each case, the learning curve was paid for in bodies. March 1910, Southern Railway Yards, Washington, D.C. Thomas Breslin climbs onto Locomotive 1102 for a routine inspection. The boiler that kills him was simple. It was also a bomb waiting for ignition. The only questions were when and who would be standing close when the metal finally failed. In the race between efficiency and safety, efficiency won. The prize was paid in lives that can never be reclaimed, in families that can never be made whole, in a debt that remains unpaid because the dead cannot present their bill for collection. I'd love to hear your thoughts. Please leave a comment below and give this video a like if you enjoyed it. See you on the next one.